Welcome back everyone, Patrick here, moving on to another word problem dealing with quadratics. Now this over here, just as a heads up, you don't have to write all of this out. Hopefully you're watching this on the website and there are lecture notes. There's a PDF of lecture notes you can print out where all these questions are written out. If you're watching this on YouTube, you can go to the website where the lecture notes are located. There's a link in the description box that will take you there. So let's see what we're dealing with here. So we're told a goalie kicks a soccer ball from a height of 1 meter, and then the ball reaches a max height of 49 meters. So in part A, we're told if the max height is reached at a horizontal distance of 4 meters, we have to find the equation of the height in relation to the horizontal distance. In part B, if the max height is reached at 2 seconds, find an equation of the height in relation to time. And then in part C, we got to take those two equations that we have, and then we have to find the approximate time and horizontal distance when the ball actually hits the ground. So with these kinds of questions, where a ball is either thrown or kicked, it's a common type of scenario. You can have the height in relation to a few things. So in this particular question, it's going to be in relation to two different things. So we're actually going to have two different graphs, two different equations. So you can have the height in relation to the horizontal distance, okay, and that's what's going to happen in part A. But you can also have the height in relation to time after the ball is kicked. So that's another type of scenario that can come up. And so I just decided to combine two. I decided to take the same scenario, but deal with one part being the horizontal distance. That's what the independent variable is going to be, or the x, and then time being in the other part. That's going to represent x, the independent variable. Okay, so we're going to start off with horizontal distance. That's what we're starting off with in part A. And what we can do is we can draw a graph with whatever information we currently have. We can draw like a general graph. So we're told a goalie kicks a soccer ball from a height of 1 meter. So whether you're dealing with horizontal distance or time here, this is always going to be height, this y-axis. And so the 1 meter, that's going to be over here. Okay, so the ball is kicked from 1 meter. So at a horizontal distance of 0 or at a time of 0 seconds, that's where the ball is starting its path. And then what happens is the ball is kicked in the air and then it comes back down. Now we're told that the maximum height, which is over here, that the ball reaches is going to be 49 meters. Okay, so both of these characteristics are going to be there. They're base characteristics, whether we're dealing with horizontal distance or we're dealing with time in the x-axis. And now, going into part A, into those specifics, we're told that the ball reaches a max height at a horizontal distance of 4 meters. Okay, so if we're letting x be the horizontal distance, or this axis be the horizontal distance, then the max height is reached at a horizontal distance of 4. The horizontal distance being the horizontal distance from the goalie, right, where the goalie is kicking the ball. And so from here, we actually have enough information to create an equation. Because notice that we're given the coordinate of this. This is 4 and 49. And we're also given this coordinate over here, right? This is like the y-intercept, quote unquote. In this case, it's like the h-intercept. And this coordinate is happening at 0 and 1. And so notice we're given a vertex and we're given a coordinate. And so it just becomes like one of those questions before where we just had to find the equation of a quadratic, right? Given a vertex, given a point. So what I'm going to do is I'm actually going to introduce some variables here. So I'm going to let h equal the height of the soccer ball. And I'll let x equal the horizontal distance. And then if you want in part B, this is also going to be in meters. In part B, you can let x also be the time, and then you'll just have two different equations where the x means something different. But I'm going to introduce another variable. I'm going to let t equal the time after the kick. So we'll use different variables. The h will be used for both part A and part B, right? Because that height is staying the same. But in part A, we'll use x as the horizontal distance. For part B, we'll use time after kick in seconds as the variable. We'll use a variable t. So again, we're starting with part A. Notice that we're given the vertex. So what we can do is just in general, we can put this in that vertex format like that. So we will have h equals a, x minus 4, right? Remember that over here, the vertex is h and k, right? So in this case, the h is like the 4, the k is like the 49. So taking that, plugging it in here, x minus 4 squared plus that k value of 49. All right, so we have a part of the equation done here, but we still have to solve for that particular a value. The way we could do that is we could use this other coordinate, 0 and 1. So we could plug in 1 for h. It has a height of 1 meter when the horizontal distance is 0, right? When the goalie is actually kicking the ball. So we would put 0 over there, then we'll have plus 49 like that. And so now notice we have an equation with just one variable to solve, that a value. So let's bring the 49 over. We'll have 1 minus 49, and then we'll have a. This will be negative 4 to the power 2. This will be negative 48. Then we'll have this, negative 4 to the power 2 is 16. So we'd end up with 16a equals negative 48. And then what we can do is we could divide both sides by 16 here to get the a by itself. So we'll have negative 48 divided by 16, which would give us negative 3. That is our a value for part A for the equation where we're relating the height to the horizontal distance. Okay, so taking this and then let's just plug it in over here. That ends up being the equation for part A right there. All right, so now we have the equation for part A. So now let's move on to part B. And what we're going to be doing in part B is we're going to be relating the height to the time, because we're told that the time that it reaches that max height of 49 meters happens 2 seconds after the kick. So what we want to do in this case is I'm going to keep this graph over here, and then I'm just going to create that new axis. But if you like, on your paper, you could just draw a completely new graph, right? So you could have the original one with the horizontal distance for part A. Now we're going to have a new graph for part B. And in this case, we're going to have time over here as the x-axis. So the only thing that's going to change is this over here. So we're told that the max height is reached in 2 seconds. So this here is in seconds. You should put the units here. Forgot to do that. Right? So 2 seconds after the ball is kicked, it reaches a max height of 49 meters. So now in this case, when we're dealing with time as that independent variable, the vertex is 2 and 49. However, notice that the y-intercept, it doesn't change, because this is still the height and the ball is still kicked from a height of 1 meter. That's the initial height. And so whether this is horizontal distance or time, at a horizontal distance of 0, it's 1 meter, and also at a time of 0 seconds, the initial height is going to be at 0 seconds. The initial height is 1. And so that coordinate actually stays the same for both scenarios. So the only thing that's changing is this 2, which is changing that vertex, but it's still a max height of 49, so that y value of the vertex is staying the same. So the axis of symmetry is different. That's the only thing that changes. But the exact same thing is going to happen. We're going to do the exact same process, but now instead of dealing with x, we're going to be dealing with time, right? We introduce this new variable, so we'll have t minus 2 to the power 2 plus 49. And then same thing, we still have to solve for this a value, so we'd be using this same point, 0 and 1. So it has a height of 1 meter at 0 seconds. Like that. And so now we just got to solve for that a value, so bring the 49 over like last time. This here is going to be negative 2. That's going to be to the power 2. 1 minus 49 gives us negative 48. And then this negative 2 to the power 2 gives us 4 times a gives us 4a. And then from here, we just have to divide both sides by 4 to get that a by itself. And when we do that, we'd end up negative 48 divided by 4 gives us negative 12. So negative 12 ends up being the a value in this case. Okay, so what happens here is this. We just got negative 12 over here. And so that right there ends up being the equation for part B. All right, so notice that it's a different a value when we're changing that independent variable, okay? Because before, this was happening at 4 when this was horizontal distance. Well, now the max height is happening at 2, which is a completely different graph, okay? So it's not the same graph. That's why I mentioned that you want to draw both on your paper. So now what we got to do is in part C, we got to find the approximate time and horizontal distance that the ball is going to hit the ground. So notice that we have the time graph here. So what we're trying to solve for is this time over here. When is it going to hit the ground? And then also bringing that other graph back. Let me just draw a rough graph here. So this is still at 1 meter. So when this is height and then this is the horizontal distance, we also have to find the horizontal distance when it's hitting the ground. So we're going to be solving for that x value in this equation. Okay, so we're going to use both graphs, both equations, to solve for the time and the horizontal distance when the ball is hitting the ground. So let's go in order here of the equations of part A and B. So we're first going to start with this graph, solving for this x value, and we're going to be using this equation from part A. Now, how do we solve for this x? Well, notice, what's the height going to be at this point? Well, the height is just going to be 0. So what we can do is we could take this equation here, and we could plug in 0 for h. And then notice that all that's left to solve for is this x value, right? And that x value is going to be the horizontal distance when the height is going to be 0. We're actually going to get 2 x values, and I'm going to explain why in a second. But let's go through this process here. So what you want to do here, first bring the 49 over, so you have 0 minus 49, which gives us negative 49. And then we'll have negative 3, x minus 4 to the power 2. Then at this point, you want to divide by negative 3, both sides, to get rid of this over here. Negative 49 divided by negative 3 would give you approximately, it'll be positive 16.33. It'll be 3 repeating, but let's keep it to 2 decimal places. And then we'll have the x minus 4 squared over here. Then at this point, you want to get rid of this exponent over here. So the way you could do that is you could square root both sides. And so at this point, this is where the two solutions come, because over here, the square root and the squared, those cancel out. So you're just left with x minus 4 here. But the square root of 16.33, That's equal to 4.04 if we round to 2 decimal places, but it's plus or minus 4.04, right? The square root of a positive value is always going to be plus or minus. And so there's going to be two solutions here, and the reason why is because if you forget about the word problem and just look at the quadratic, the abstract quadratic, well, a quadratic is just going to continue to extend out infinitely, right? And so notice that there's going to be another intercept over here. So there's actually two values in this quadratic where that height is going to be 0. However, because we're dealing with a word problem, okay, we're not going to have a negative horizontal distance and we're not going to have negative height, so we're only looking at this portion of the graph. Okay, but when you're doing this algebra here, you're still just working with that abstract quadratic, and so you're going to end up getting these two solutions. But this solution here, which is going to be negative, you could tell from the diagram, you'll just ignore. But just want to mention that. So there's two cases here. So either positive 4.04 equals x minus 4, or negative 4.04 is equal to x minus 4. Bring the negative 4 over, so you have negative 4.04 plus 4, which gives us negative 0.04. That's where the negative value is going to come in. And then over here, bring this over, x would be 8.04, right? So this here ends up being negative 0.04, but that's not a valid value in the word problem, so we would ignore that. And then the other x value is going to be 8.04. Okay, so for part C, the horizontal distance when the ball hits the ground is 8.04 meters. Right, and this is the algebra that you go through in order to get that. Now, what about the time that it hits the ground? So now we're going to be using this graph and then this equation, but we're going to do, it's going to be the exact same process. You know what, I'll just erase this graph as well. Won't be using it. So now what we got to do is we're going to solve for this time. And we're going to be using this equation, right? This graph is represented by this equation. Now, like in the previous calculation, we're actually going to get two values here because, again, this extends, right? So there's another intercept here where that h is 0, but it's going to be negative, which would be a negative time, which wouldn't make sense in this case, so we're just going to ignore that negative value. But we are going to get two values again, right? So what we would do in this case is we would say 0, again, we're solving for the time when the height is 0. Then we'll have negative 12, t minus 2 squared plus 49. And then same thing, same algebra. So bring the 49 over, so I'll have negative 49, negative 12, t minus 2 to the power 2, divide both sides by negative 12. And then negative 49 divided by negative 12, that's going to give us 4.0833 approximately. And then we'll have the t minus 2 to the power of 2 by itself. And then same thing, this exponent you want to get rid of, so we square root both sides. What you do to one side, you got to do to the other. These cancel out, so we're just left with a t minus 2 over here. And then the square root of this is approximately 2.02. I'll just round it to 2 decimal places, but you could keep more decimal places if you want. And then because we're square rooting, this is going to be plus or minus. So that's where those two cases come in. So either this t minus 2 is equal to positive 2.02, right? So either t is 4.02, or the other case is the t minus 2 is negative 2.02. Bring this over, and we get a negative value. So that's where that negative is going to come in, but we would just ignore that in this word problem. Okay, but just in case maybe you're dealing with an abstract quadratic, you get a question where they're asking for the intercepts in this kind of format. This is the calculation you would do, and then you'd have to include both values that you get, right? So this 4.02 ends up being the time that we're looking for. So that's the answer to part C. So the time after the kick, when the ball hits the ground, it's going to be 4.02 seconds. All right, so pretty unique question, pretty cool question in terms of taking the same scenario but changing up that independent variable. It could be horizontal distance or it could be time. That's how you can create the equations, and then once you have the equations, you can get different characteristics, including the time and the horizontal distance that the ball hits the ground.